there are a few different views of multiplication that I want to talk about. The first one being repeated addition or groups. So I like to think of multiplication typically as like groups of some size. So here I have a bunch of purple dots, and we've highlighted them to show that they can be viewed as three groups of 4 dots. So this represents the multiplication problem 3 times 4. You could represent the same number of dots using 4 groups of 3 instead. So here we have 4 groups of size 3. So I think of this as like A times B is representing A groups of size B. Okay. One thing that should maybe stick out to you is that from this approach, it's a little bit hard to see just visually that these represent the same number. They both represent 12 dots. Like if you were to group them all together into like one giant clump, there'd be 12 dots, right? But it's a little bit visually harder to see. So another approach that you could take is called the rectangular array approach, where we say that A times B represents A rows of B columns. So here I have 3 rows of 4 columns, and here I have 4 rows of 3 columns. Or I think I said that wrong. 4 rows by 3 columns, or four rows of 3 squares. You could actually view this as like in a similar way. Here we have like 3 groups where each group has 4 blocks in them, and here we have 4 groups where each group has 3 blocks in them, kind of similar to the previous one, right? But it's a little more obvious why these visually represent the same number, because you could just rotate this guy and exactly get the second guy. Okay, so this is visually highlighting the commutativity property of multiplication, meaning that 3 times 4 is the same as 4 times 3, or really for any pair of numbers, A times B and B times A are the same. Whereas this previous view, A groups of size B, tends to be more useful for interpreting multiplication in most situations, like most problem solving situations. So this one tends to be like really useful for like applications of multiplication. This one is good for sort of understanding multiplication. So some properties of multiplication are as follows. There's a closure, commutative, associative, identity, and distributive properties of multiplication. And all of them are pretty important to understand for different reasons. So the closure property of multiplication basically just says that if A and B are whole numbers, then A times B is also going to be a whole number. All right, if you did 3 times 4, 3 and 4 are both whole numbers, and 12 is also going to be a whole number. Okay, and that's always going to hold. That should be intuitively obvious. The same property holds for like addition as well. If you were to take 2 whole numbers and add them together, then you would get another whole number. But that does not hold for, say, like subtraction or division. If you took 3 minus 4, this would be -1, which we do not consider a whole number. We consider that, it's called an integer. And if you took 3 divided by 4, this is like 3/4 or 0.75, this is not a whole number. So closure is a property that holds for multiplication, but not necessarily all other operations. Commutative, we just talked about, just says that essentially order doesn't matter, and you can see that from the rectangular array approach very easily. The associative property says that if you're multiplying 3 numbers together, so say like 3 times 4, and then multiply that by 5, it actually doesn't matter which order you choose to multiply them in. You could multiply them left to right, you could multiply them right to left. The order will not matter. Effectively, what that means is that if I were to write down a string like this, 3 times 4 times 5, parentheses are really not needed here, because like an order is not implied here, but the order in which we decide to multiply these numbers does not matter. Like I could even multiply like 3 times 5 first and then multiply that by 4. That would be like due to the commutative property as well. But the order in which we multiply numbers does not matter, which is in stark contrast to if you were to say, start including like some subtraction or division here. If I took 3 minus 4 minus 5, it's not clear if this should mean 3 minus 4 minus 5 or 3 minus 4 minus 5. These are going to represent different numbers, because this is -1 minus 5, which is -6, and then this is 3 minus -1. 3 minus -1 would be +4. So these represent different numbers. And so parentheses are important for things other than multiplication, but with multiplication, order doesn't matter. This actually ends up being a really useful property too, to know how to use flexibly when it comes to computations, and I'll show you that in a minute, along with the distributive property, which is also really useful. The identity property is less useful, but it's important to understand that 1 is the multiplicative identity element. If you were to take 1 times any number, then that's always going to give you that number back. Similar to how 0 is like our additive identity number. If you take 0 and add it to anything, you're always going to get that same number back. And the distributive property just says that A times B plus C is A times B plus A times C. So this ends up being really useful for computations as well. So let's see some examples. So if I wanted to do, well, here's just like a bunch of them that I have. So 31 times 4. I could think of 31 times 4 as 30 plus 1 times 4. And then I could just do the distributive property to distribute this 4 to both of these numbers. So this would be 30 times 4 plus 1 times 4. This is literally what the distributive property says. So this is 120 plus 4. And this is actually a lot harder to do in your head than if you were to understand how to do this with the distributive property. So even if I didn't have this stuff over here, I can understand 31 is 30 plus 1. So I should do 30 plus 4, 30 times 4 plus 1 times 4, and 30 times 4 is 120. 120 plus 1 times 4, 124. So that becomes all of a sudden something that I can do in my head much easier. You could do that for 15 times 20 as well. There's this one, there's like a bunch of different ways that you could do this. So maybe you could do this as 15 times 10 plus 2. So this would be 150 plus 30, which would be 180. And that's just coming from the distributive property. We distribute this 15 to both terms. And now this is 150 plus 30, which is 180. Okay, so again, distributive property makes things a lot easier to do in your head. And you can go backwards too. 8 times 7 plus 2 times 7. So basically we have 8 groups of 7 and then another 2 groups of 7. If we have 8 groups of 7 and then 2 groups of 7, all together we have 10 groups of 7. So really what's going on there is we're like reversing the distributive property by, this is really factoring, right? Think about it, this is like what we call factoring out a 7. And all of a sudden we have 10 groups of 7. Which is 70. So instead of having to do actually 8 times 7, which is 56, and then adding 14 to it, and then trying to figure out what 56 plus 14 is equal to, all of a sudden this becomes 10 times 7, and that's a lot easier to do in your head. Okay. 5 times 15. This is a problem where the associative property is really useful. You could also do the distributive property again by like maybe doing this as 5 times 10 plus 5. So this would be 50 plus 25 is 75. But let's see how we can do the associative property to do this instead. So the associative property, we could break 15 up as 5 times 3. And so if we represent 15 as 5 times 3, then we have this problem is the same as 5 times 5 times 3, which is the same as 5 times 5 times 3 like this. And so 5 times 5 is 25, and then 25 times 3, that's, to me, easier to do in my head than like 5 groups of 15. So adding 15 to itself 5 times versus adding 25 to itself 3 times, to me, this is easier. Let's go back to 15 times 20, because that's another good application of the associative property. So 15 times 20, so I could break this 12 up as, so this is even, right? So I can like break this up as like a 2 and a 6. And so now I could just multiply this 2 by 15, and that makes 30. So now I have 30 times 6, which is 180. So that, again, is much easier to do in my head. Okay, and there's like many ways that you could go about doing this too. Like this is, you could also break this up as 15 times 4 times 3. 15 times 4 is 60. And that's also going to give us 180. So yeah, the more that you understand these properties and how to utilize them, the better your number sense is going to be, and the more flexible you're going to be when it comes to computing all of these different types of problems.